All right, so here is the same problem, but this time I've restricted the domain. So if you notice, f of x is equal to x squared plus 2, where x is greater than or equal to 0. So if I go through and actually do the algebra, okay, so step 1, we're still going along with the steps from the first slide, where we replace f of x with y. So that's what I did right here. I went ahead and still wrote down the restriction. Second step was to interchange x and y. And notice that I did that here. I swapped out x and y. Third step was to solve for y. Notice that I went ahead and solved for y. I put y squared plus 2 on the left and went through the whole solution process. First, I subtracted 2 from both sides. And then since I was left with y squared, to undo squaring, the inverse operation of that is square rooting. So I square rooted that side. Well, what I do to one side, I have to do to the other. So I had an x minus 2 on this side, and I square rooted that. And so on the left side, we're left with y equals, we have plus minus the square root of x minus 2. Now, this is the important part here. Since x is greater than or equal to 0 for f of x, then y is greater than or equal to 0 for the inverse relation, because remember, we have to interchange our x and y values. So y equals positive square root of x minus 2. So we need to get rid of the negative as one of our possible equations for y. And so then we can write the following. Y is equal to the square root of x minus 2. So this is different than what we had over here. We weren't able to cancel out one of them because we didn't have a restriction on the domain of f of x. We didn't have that restriction there. So that's the nice thing here. So now, since we have the restriction, we're able to cancel out the negative equation. And so then we can go ahead and proceed to step 4. Step 4 says that if the equation for y represents a function, then we replace y with f inverse of x. And so we have f inverse of x is equal to the square root of x minus 2. Then we proceed to step 5. Step 5 is where we go ahead and compose, right? We want to check that f of x and f inverse of x are indeed inverses. So we compose them with each other. And we want to make sure that when we compose either way, if we take f inverse of x and put it inside f, or if we take f of x and put it inside f inverse, that we get an output of x. And so you can see from the work, if you want to just kind of look at this slowly, you can, but we do indeed get x as an answer in each case. I do want to show you here on the second one, when I have f inverse of f of x, as I go through the solution process, I end up with the square root of x squared. By definition, the square root of x squared is equal to the absolute value of x. Now I'm going to write something down for you. I didn't write it here, but I'm going to go ahead and just do that real quick. So we have a piecewise definition for the absolute value of x, okay? And I'll just write it up here. So the absolute value of x is equal to negative x whenever x is less than 0, and positive x, or you can just say x, whenever x is greater than or equal to 0. So notice here that the domain we chose was x is greater than or equal to 0. So we're going to choose the second piece of our piecewise function for absolute value of x. So that's why down here in part of my little verification that they're inverses, that the absolute value of x is equal to x there. Okay, and I wrote it there, but I just wanted to show you it's based off this piecewise definition. All right, so that's the entire process of getting the equation for f inverse of x and just showing that it is an inverse. But the main thing to understand here is that you have to restrict the range if it's not 1-to-1. So now that we've shown it algebraically, let's go ahead and look at our graph. Here is f of x. Notice that it's restricted from 0 to infinity, or we say x is greater than or equal to 0. And then reflected across the line y equals x, you can see f inverse of x, a nice mirror reflection across, and it's restricted. Now, the domain isn't restricted from 0 to infinity, but the range is restricted from 0 to infinity. In fact, that should make sense when we talk about inverses. If you're switching out x and y, well, the domain and range are going to be switched. So I think that's something I hadn't mentioned in the video, but that's going to be what happens there. And so we can talk about that here, and I'll add that to my notes as well in just a second. But so notice here that the range for f of x is from 2 to infinity, or we can say that y is greater than or equal to 2. And while the domain of f inverse of x is from 2 to infinity, or we can say x is greater than or equal to 2. So the range and domain switch there as well, you can see. So in this case, the range of f of x became the domain of f inverse of x. But that will always be true for inverse functions. So let's go ahead and add that as an important note. All right, so here we have it. The domain of a function is the range of its inverse relation, and the range of a function is the domain of its inverse relation. So they get switched out. In this example, the domain for f of x was from negative infinity to positive infinity, as was its range. So notice the inverse also has a domain from negative infinity to positive infinity, and it also decreases down to negative infinity and increases to positive infinity. So it has the same range as the domain of f and the same domain as the range of f. Notice over here for f of x, when it wasn't restricted, well, the domain was from negative infinity to positive infinity, whereas the range for the inverse relation was from negative infinity to positive infinity. The range for f of x was from 2 to infinity, whereas the domain for the inverse relation was from 2 to infinity. So even though our inverse here wasn't a function, it's just a relation, it still swaps the domain and range values with the function. All right, let's get back to our example with this restricted domain. So I think the only thing that we haven't looked at is just the table. So I went ahead and took away those negative points that we had in the domain for the original. If you notice, we had -2 and -1 there. They're no longer there because we're starting at 0. So we just have the point 0, 2, 1, 3, and 2, 6, these 3 points. When we swap them, we have the points 2, 0, 3, 1, and 6, 2. Those are there. And so, the properties that you look at for a table, notice that no two y's are repeating for the original function. So it's 1-to-1, which means it's invertible. It has an inverse function right here. And this is indeed a function, at least based off the points that we see right here, right? There aren't any x's repeating. The only thing that I had left to show you on the graph was that now our inverse relation passes the vertical line test, so it is a function. So we have an inverse function. And you can see that also the original function f of x passes the horizontal line test. So again, just to reiterate, if the function passes the horizontal line test, then its inverse is going to pass the vertical line test. Well, that brings us to the end of this lesson. I hope that after going through all of this information, you have a much better understanding and you feel more comfortable when working with functions and their inverses. Have a good day.